Hello. Alright. Welcome back. Today we're going to be talking about simple machines, and specifically what simple machine? Levers. If we're going to talk about levers, we got to talk about moment. And so today you're going to learn about moment. You're going to learn how to calculate moment. We're going to calculate missing distances or weights or some type of force or on the object on a lever. So let's talk about moment. Moment is the turning effect of a force about a point equal to the magnitude of the force times the perpendicular distance from the point to the line of action from the force. So moment is force times distance. It is, again, it says is equal to the magnitude of the force times the perpendicular distance. So what they're telling us here then is that this force right here and this distance, all right, have to be perpendicular to each other for a moment to happen. Because of that, this force would cause it to turn counterclockwise. But on the other side, we also have a force. This box is applying a force down. It is some type of distance away, and it would also cause it to spin, except this spin or this turn would be a clockwise movement. Now the other thing I want to address here is this little object right here, and this is what we'd call the fulcrum. That is the point at which it's going to be turning at. Now the reason we're going into momentum, or moment, not momentum, is because we have this force times distance, and we just got done talking about work. Work, we said, was force times distance. So what's the difference between work and moment? Because the equations are exactly the same. The only difference here is that for work, the two had to be perpendicular. Or for work, they had to be parallel. For moment, they have to be perpendicular. All right? And this perpendicular force and distance, this moment, creates a torque. All right? A torque is a force that produces or tends to produce rotation or torsion. And as we talked about, this force over this times this perpendicular distance will start to cause it to rotate, whether it's counterclockwise, or this force and distance over here will cause it to rotate in a clockwise direction. Alright, so when it comes to levers, one of the first things I always teach students to do is to separate this side into two sides. So I'm going to draw a line right through the fulcrum. On the right hand side we have what's called the resistance, because the box is going to represent resistance. This would be an object we were trying to lift. On the left hand side, this arrow is going to represent, not always on the left, but the arrow is going to represent the effort or how much force we're putting into it to lift the box. All right, now the box could be anything, but we're just using the box as something as generic. So let's label a few things. Well, on the effort side, we have two things. We have effort distance and effort force. Well, we call these DE and FE. So this up here would be my distance effort. This right here would be my effort force. On the right hand side, for underneath resistance, we have resistance distance and resistance force. Well, up here, this would be my resistance distance, so we'd call it dr. And this right here, this box, is my resistance force, so we would call that fr. Now the next thing I want you to realize is that for all levers, we're going to assume that these two sides, or these two moments, are equal to each other. So what we do is we set the moment of the effort equal to the moment of resistance. So let's use our equations that we know. All right, FE, DE is going to be equal to FR, DR, and that's just going back to our moment equation right here that we had, that we gave to you right away. Now we've got our equations in here. Let's plug in the numbers that we know. The effort force was 15. The effort distance was 5, so we're going to multiply those two. On the right-hand side, our resistance force is 25, and we do not know the effort distance yet. It's a question mark up here. So we get 75 equals 25 times dE. Well, divide both sides by 25 and you get 3 equals dE. Well, 3 what? Well, the left-hand side was in inches, so our answer over here is going to be in inches as well. Without going into a whole lot of reason why, we'll go over that in class. Alright, let's go to another problem here. Okay, some things I've already given you here. I've already wrote this part of the equation down here. The effort moment is equal to the resistance moment. Fe times dE is going to equal to Fr times dr. So now we've got to identify what these things are. So here's my effort side. Here's my resistance side. So I've already got my line drawn in here to separate these two sides. So on the resistance side, this right here is my resistance force, because it's the box. The box is the resistance force. We make it real simple to start off with. And then this up here is my resistance distance, which we do not know, so we're going to solve for it again. 5 pounds, this is on the effort side, so I'd say that's Fe. This right here is dE. Now it's just a matter of plugging them into the equation. Well, over here, Fe is 5. dE is 10. Fr is 25. dr is what we're going to solve for. 5 times 10 is 50. 25 dr. So we find out then that the resistance distance, or dr, is 2. If you divide both sides by 25, you get 2. Well, what was my effort? Effort was in inches. My distance resistance is going to be in inches as well. So this box, if it was 2 inches from the fulcrum, would be allow this lever to stay balanced if we applied a force 10 inches away from the fulcrum that had a force of 5 pounds. Alright, again, I've got this side labeled as my resistance. It's on the side of the box. I've drawn my line to represent, or to split my resistance, and this side over here is my effort. Alright, this is my effort side because it's got the arrow. So let's identify these sides and find our missing information. In this case, we're going to be finding the missing force. So this right here is dr. This right here is Fr. This is Fe. And this right here is dE because it's on the effort side. Things on the resistance side have to be something R. Things on the effort side have to be something E. So let's plug in what we know. The effort force is 6. My effort distance is 20. On the right hand side, my my resistance force, I don't know. My resistance distance is 5. 6 times 20 is 120. Over here I get 5 times my resistance force. Divide both sides by 5, you get 24, and it's going to be in pounds, equals my resistance force. Alright, we've got one more problem here. So as I look at this here, oh, I erased this by accident last time. Didn't mean to move that. Close enough. I had it on here. Come on, there we go. That's 2 pounds. So, this over here, because it's my box, is my resistance side. This over here, because it's my arrow, is my effort side. So I've labeled those two sides. Now let's label our things that are given to us. This is my resistance force. This is my resistance distance. This is my effort force. This is my effort distance. Put a D down there, not an F. So now it's time to plug in what we know. This is going to be 2 times dE. My resistance force is 10. My resistance distance is 3. So I get 2 times dE equals 30. Divide both sides by 2 and my effort distance turns out to be 15. What's my units? Well, it's in feet over here, so it's going to be 15 feet. Alright, this is the last thing you guys got to do here today. I want you to draw this picture and identify the effort distance, the effort force, the resistance distance, the resistance force, and the fulcrum. Hey, I hope that was informational for you guys. I'll catch you on the flip side.